Welcome to the new year of the CRM Montreal Quebec Analysis Seminar. Our first speaker is a new faculty member at Concordia, Maria Ntekoume, or Ntekoume, who is going to speak on critical well-posedness for the derivative nonlinear Schrödinger equation on the line.
Great. Thank you very much for the introduction. I can also say thank you for the invitation, although I'm also an organizer of the seminar, so I don't know how much I can include myself in the thing. And of course, thank you all for being here either in person or on Zoom. Okay, so as you can see from the title today, I'm going to talk to you about some joint work with Ben Harrop-Griffiths, Rowan Killip, and Monica Visan on the derivative nonlinear Schrödinger equation. So the first thing I should do is show you what equation I'm talking about. So here it is, our equation. So, okay, I can hide myself from the Zoom 1 second to show you that we have here a linear part that is the Schrödinger linear part. So we have I times the time derivative of q plus 2 derivatives of q with respect to space. So whenever I write prime, it means derivative with respect to my spatial variable x. And then we have a nonlinear part that is cubic, and it also has a derivative. Okay, so here we have two variables, the time and x, a spatial variable, and we're going to consider x being in one dimension and on the entire real line. So we consider this equation, the derivative nonlinear Schrödinger equation, with some initial data Q0 that will be in some Sobolev space, which Sobolev space that will be something to be discussed later. So this equation arises as a model in plasma physics.
So I is a constant?
Yes, yes. And it's a, the usual line. It's no surprises
imaginary unit.
Oh, the imaginary I?
Yeah.
Oh.
Square root of -1. In engineering, they actually write square root of -1 exactly for that reason.
That's it. Okay. So what are we interested in this talk regarding this equation? We're interested in investigating the well-posedness. So does the solution exist? Is it unique? And do we have continuous dependence of the solution on the initial data? Okay. So before we start doing anything, let me tell you a few general things about the derivative nonlinear Schrödinger equation. So in general, for when we have a dispersive PD like this one, the first thing that we do is investigate if we have some scaling symmetry, and we do. So if I take Q, that is a solution to DNLS, and rescale it like that, okay, so if you look back at the equation, you can see that one derivative in time is like two derivatives in space, and that's why I have here lambda squared multiplied by t, and then lambda x to balance things out, and the square root of lambda multiplied in front has to do with the fact that they have this cubic nonlinearity with the derivative. So if I rescale my solution like that, then this q lambda is also going to be a solution to the NLS for any parameter lambda that I choose. And when we have a scaling symmetry, that gives rise to a notion of criticality. So we ask ourselves,
Question, sorry, I cannot do it in my head, but
Yeah.
without the derivative, standard NLS has
Yes.
a different scaling or has no scaling at all?
yeah, it has a scaling, but it's different, right?
So-
Because it's with a derivative, you get this extra lambda multiplied in the front.
And so there is a different in critical.
Yes,
Okay.
exactly. Okay, so when we have a scaling symmetry, we ask ourselves which norm is left invariant under that scaling. And in this case, it is the L2 norm. So if I take the L2 norm of the rescaled solution, it's going to be exactly the same as the L2 norm of Q. And for that, we call the problem L2 critical. And the long-standing intuition in dispersive PDs is that if I consider the problem with initial data with more regularity than the critical one, then I expect things to behave well, to have well-posedness. I expect things, at least my argument, the proof to become harder and harder as I approach the critical regularity. And then once we go below the critical, in the supercritical regime, we expect things to blow. Okay. So in some sense, what we expect is that the critical is the best possible and hard, okay? For this problem, the L2 norm has also another significance. It is preserved under the flow. So the L2 norm at any time t is going to be the same as the L2 norm of the initial data. And in fact, this equation has many, many more conserved quantities. It has infinitely many. So I have written down some of them. We have the square of the L2 norm here, mass. We have the energy. And we have many, many more. I cannot write them all down, but what they have in common is that they all look like integrals of some polynomial of Q and its derivatives, and they have more and more derivatives as I keep going down. And that is one feature of completely integrable equations, and the NLS is one of them. Okay. So from what I've said so far, we see that investigating the well-posedness of the NLS in L2 is an interesting problem, the best that we could hope for, and it is going to be hard because it is, as we said previously. So we make the conjecture, the NLS is globally well-posed in L2. Now, let's see whether this conjecture is promising or not, whether we believe that it will be true or not. So we can, let's look at some equivalent models to the NLS. So let's say I have Q that solves the NLS, and then I transform it like this, okay? So I take U of the NX to be Q T negative X, right? So I switch the order of the real line. Then this new solution, this new U is going to solve not the NLS, but an equation that looks awfully similar. The only difference is that my plus sign here of the nonlinearity has been replaced by a negative sign. Okay, now you might be wondering, well, why do I care if it's a plus sign or a minus sign? Well, one, on top of the criticality of the problem, another feature that we care about in dispersive PDs, or that we can use as an indication of whether our problem will be well-posed or not, is whether the problem is focusing or defocusing. So in other words, if the nonlinearity is helping the linear flow or if it is working against it. And for the non-derivative, for the standard nonlinear Schrödinger equation, we can tell that from the sign of the nonlinearity, if we have a plus or a negative sign. But here for the NLS, we see that both the plus and the negative sign are exactly the same, right? I can transform one to the other without a problem. So that makes us worried, right? Because, well, if one is focusing, the other one is as well, right? Another negative sign towards this direction is the following. So if I take again Q, a solution to the NLS, and do a Galilei transformation to it, then I will get V that solves this equation. So what do I have here? I still have a cubic nonlinearity with a derivative, but I also have a cubic nonlinearity without a derivative, multiplied by factor K, which can be anything I want, positive, negative, huge, small, right? So in particular, we can see that in some sense, the cubic nonlinear Schrödinger equation without the derivative is in a sense embedded in the NLS. And I can have here a very, very large negative sign, which would be bad, right? Which would be the focusing case. Okay. And another transformation that I can do to a solution Q to the NLS is the following, where W, I mean, I'm not showing you, it's okay if you don't have enough time to read what the transformation I'm doing is. If I do this though, I will get W that solves this complicated equation where what we have some terms that are cubic with a derivative, but we also have a term that is quintic without the derivative, right? And why is this bad? Because if I take nu to be very, very large, I would expect that this part, this quintic term dominates, right? And that would be the quintic NLS, which is ill-posed in L2. Okay. I mean, the focusing quintic NLS, which is ill-posed. Okay. So that doesn't sound very encouraging. So what was known when we started looking at this equation? When you try to study well-posedness, the first step is understanding the local well-posedness. So for this equation, local well-posedness was known in HS for S greater or equal to 1/2. So quite far from the L2 that we are interested in. And together with that, there is an well-posedness result that tells us that actually once you go below S equals 1/2, you cannot have uniformly continuous dependence on the initial data. And you might say, okay, that's not too bad. I can still have just continuous dependence on the initial data. However, this immediately rules out a lot of methods that you have at your disposal to study dispersive PDEs. In fact, most of the methods that we have available can only produce results where you have uniformly continuous dependence in the initial data. So we would have to think in a different way. So when we started looking at this problem, there was no local well-posedness known below H1/2. Okay. Then, if you want to go from local well-posedness to global well-posedness, what you do? The result that I mentioned, the first one here, actually gives us an estimate for the time of existence. It tells us that the time of existence is going to depend on the H1/2 norm of the initial data. So here's an idea. Well, I have all of these conservation laws, right? They all have derivatives of Q, and actually one of them looks very similar to an H1/2 norm of the solution. So perhaps we can think, okay, I have conservation laws, perhaps I can leverage them to get some a priori H1/2 bounds. And then if my solution is uniformly bounded in H1/2 at all times that it exists, then I can iterate this local well-posedness result, glue the solutions together and have global well-posedness, and then I will be happy. The problem here is that the conservation laws cannot be used to get a priori H1/2 bounds because they are not coercive. So this strategy will not work. So what did people do to overcome this problem? Was restrict ourselves in a regime where we have coercivity. Okay, and that was done by assuming something more about the L2 norm of the initial data. Yes.
I'm assuming that somebody here may not remember or know what coercivity means.
Okay. Okay, so I cannot use the conservation law to bound my H1/2 norm.
But is there something, conservation law are not bounded from below? Is something related to that? No, you say not?
They can change sign.
Yeah, okay.
Yeah, so the problem is, okay, maybe if I go back here to the conservation laws, you see that here you would expect this to look, that looks a little bit like an H1/2, right? However, I have this thing which, you know, can be very, very large, right?
Okay.
So that can cause problems. Yeah. So I can bound this by the H1/2 norm, but not the other way around. Okay. So the first group of results assumes that the square of the L2 norm is less than 2 pi. And once you have that, you can actually work out the bounds that you want and get global well-posedness. And that was done successively starting from H1, then H is greater than 1/2, and then in 2011, H1/2. Okay, so it takes a while to go down to the optimal well-posedness regularity at that point, but it was worked out. Now, what about trying to make this assumption on the L2 norm a little bit milder? Well, that actually took 20 years, and it was only improved to 4 pi initially in 2013, just a little bit more than 2 pi, and then in 2015 to 4 pi. And this 4 pi here, well, you might think, okay, I just have to work a little bit smarter, right? Find the right things to do, so that the right way to combine my conservation laws so that I can get rid of this assumption. But in fact, this 4 pi here has a significance. It is the mass of a special solution of the equation, which is called the algebraic soliton. It looks like this. So you have some profile that is traveling and is also oscillating. And it is really the threshold where the conservation laws are going to lose their efficacy. And I can show you exactly why this happens. So if I take this algebraic soliton and I rescale it using that scaling symmetry that we saw before, I get the family of solutions all of these solutions, of course, have the same L2 norm, right? Because we saw that scaling preserves the L2 norm. They also have the same values for all of their conserved quantities. But then if I look at the HS norms for S greater than 0, they're all unbounded. Okay. So there is no way that I can just use the conserved quantities to control HS norms. This whole family is exactly the same for the conservation laws, but for the conservation laws, but for the HS norms, it is not at all. Yes.
Sorry, so for this 4 pi initial condition, is there nothing known for the intermediate regime there for HS as bigger than 1/2?
No, it is bigger than 1/2. Yes, it is.
Okay, so
it
there
is
are
not-
results,
yes.
so there's like a continuum down.
Yes,
towards-
yes, yes.
Okay.
Okay. On the other hand, there was a collection of results that do not require any assumptions on the L2 norm, but what they require instead is some decay in space. So, for example, here we require the solution not just to be in H2 and to be in L2, but also to decay like x to the negative half in L2. Okay. And now you might wonder, how did these results not require any assumptions on the L2 norm? And the answer is that they use very different methods. They use inverse scattering methods to do that. And that is exactly why this decay in space is required. Okay, and then very recently, there was a very surprising result by Bahuri and Perelman, who showed that actually we have global well-posedness in H1/2 under no assumptions on the L2 norm. And from what we have said so far, you can already tell that this uses more than just the standard PD techniques that I was referring to earlier, because for those, all the conservation laws cannot control any HS norms above mass 4 pi. So they use a combination of PD techniques and inverse scattering. Okay, so when we started looking at the problem, we started thinking, well, what is our enemy here? We want to study the problem in L2. L2 is a conserved quantity. So there is no fear of the L2 norm growing, right? The only fear is that the L2 norm might concentrate in space, right? So you might have something that looks like this, started with a profile like that, and then as time goes on, it concentrates more and more and more in one or more locations in space. And what can prevent that is equicontinuity. So a bounded in L2 set Q is equicontinuous if I take Q and translate by H, this will converge to Q in L2 as H goes to 0 uniformly for all Q in Q. So small translations lead to small difference in L2 norm uniform. Okay? And you see that something like this is definitely not equicontinuous, right? As I keep concentrating more and more, a small translation can cause a big difference in the L2 norm. Okay. So what do we want to show that is equicontinuous? We want to show that if I take my solution at different times and consider this set, that is what I want to see that is equicontinuous, to avoid concentrating in space. And to make it a little bit more general, which will be useful later, instead of considering a single initial data Q0, we're going to do it for a collection of initial data. Okay, so we're going to take a set Q that is bounded in L2 and equicontinuous, take all of this initial data and flow it under the NLS, and then take the collection of all what we can get at all possible times. Okay, so that is the set Q star. And what we want to show, and what we did show, is that if I start with a set Q that is bounded in L2 and equicontinuous, then Q star will also be equicontinuous in L2. Okay, and now you already see that there is a line that I skipped, which is this assumption that the square of the L2 norm is less than 4 pi, right? So in our first go at this problem with Rowan and Monica, we were only able to prove this equicontinuity result under this assumption on the L2 norm, which at least it was matching what was known at the time that we proved it, okay? But was still leaving something to be desired. Now, having this equicontinuity result, we were able to prove a priori H is bounds. So if we have S between 0 and 1/2, Q a bounded subset of HS, and this L2 norm assumption, then we can bound uniformly the H's norm of our solution in terms of the H's norm of the initial data. Okay. And finally, using the continuity in this H's bounds, we were able to prove global well-posedness in HS for S between 1/6 and 1/2. Okay, so again, not yet in L2, but and again with this assumption of the L2 norm, but definitely much closer than H1/2. And as I said, at that point, not even local well-posedness was known. Okay. So one thing I want to address is this assumption on the L2 norm. You see it appearing in these terms again and again. A very important comment is that the only reason that it appears in the H's bounds theorem and in the global well-posedness theorem is the historical continuity. Okay? So if there was a way to remove this assumption from the first theorem, from the continuity theorem, then automatically it could be removed here and here. Okay. And this is exactly what Ben, Rowan, and Monica did soon afterwards. So they were able to remove the L2 norm assumption on the continuity theorem, and as an immediate corollary, we get global well-posedness down to H1/6. Okay. But the title of my talk is Critical Well-Posedness, so you can already tell where this is going. So the four of us together decided that, okay, H1/6 is good, but we can do better. So we were able to prove global well-posedness in the critical space, L2. Okay. So now let me tell you a few things about the methods. So as I said earlier, this equation is completely integrable. What does it mean? One feature that we saw is the existence of infinitely many conservation laws. And we already saw the limitations of this feature when we want to prove global well-posedness, at least in such low regularity. Another feature of completely integrable equations is the existence of a lax pair. So a lax pair is a pair of operators L and P with the following property. If L and P satisfy, L and P satisfy this equation, if and only if Q, the Q that is plugged in here, is a solution to our equation. And the formulation of this allows us to deduce that the spectral properties of L are preserved under the flow. And then hand in hand with this, we have that completely integrable equations that meet an inverse scattering theory. So from our initial data, we can get the scattering data, and then from that, we can see how those evolve in time in a simple fashion. And then the harder part is from using the scattering data at a later point to reconstruct the solution at a later time. And I already mentioned something about this, that it requires some decay in space to formulate, to make rigorous sense of this. Okay, so you can also, once again, you can tell where this is going. I have already pointed out some problems with two of these approaches, with two of these pictures, so you know which one I will be following. Okay, so we focus on the lax operator. So here's the lax operator for DNLS written here. If you're wondering, this L here looks very similar to the lax operator for the cubic nonlinear Schrödinger equation without the derivative. Okay, the only difference is that without the derivative, we have these square roots of kappa here would be missing. Okay, and it would make the analysis much better. Okay, so this is L, and L naught is L where we plug in the potential Q equals 0. Okay. Okay, so from that, we consider the perturbation determinant like this, the determinant of inverse of L naught L. And then after some renormalizations, we end up with this object, A, okay? Which is a determinant of 1 minus I kappa lambda gamma, where the lambdas and the gammas are written down here. Okay, so we have this thing. On top of that, we're going to consider, yes.
This is, sorry, capital lambda gamma is one thing, or is a product of two things?
Product.
Okay,
products.
Oh, lambda.
Of lambda and
gamma.
gamma.
Okay,
Yes.
and I guess each of them is in the Schmidt or the at
Yes.
least, okay.
Yes. Yes. So, okay, so we have this A, and we also consider alpha, which is negative logarithm of this A. Okay. And the good thing about that is that it has this series expansion as the sum of 1 over L as a trace of I kappa lambda gamma to the alpha. Okay. Now, why do we care about that? Well, we said earlier that we expect the spectral properties of L to be conserved. And for that reason, okay, alpha is going to be, well, A and alpha are going to be preserved under the NLS. And that was already noticed by Klaus and Shiba. Okay. Now, how is this alpha going to help? So we get this new collection, this new family of conservation laws, right? I have one conservation law for every kappa, right? So I have infinitely many conservation laws. And what I claim is that these are better suited to my problem than the previously known polynomial conservation laws. And here's why. So a set Q is continuous in L2 if, as we said, small translations lead to small changes in the L2 norm uniformly. Another equivalent way to think of a continuity is a tightness in Fourier space, right? So we want the high frequency, the square of the high frequency, well, yeah, the high frequency part of the solution to converge to 0 uniformly, right? Now, alpha has this nice series expansion. I know that alpha is conserved under the NLS. And if I look at the first term, when L is equal to 1, I can actually compute what I get. So the imaginary part of this trace is the integral of 2 kappa squared over 4 kappa squared plus c squared q hat squared. Okay, this is not exactly what I want yet. So let me instead consider the following. I consider beta, which is the square of the L2 norm minus 2 times the imaginary part of alpha. Since the L2 norm was conserved and alpha is conserved, beta is going to be conserved as well. And now if I look at the first term of the series expansion of beta, the quadratic term of beta, it is going to be, I will denote it as beta 2, and it is going to be this thing, the integral of c squared over 4 kappa squared plus c squared q hat squared. Okay, and this thing really captures the high frequency part of Q, of the L2 norm, or the square of the L2 norm of the high frequency part of Q. Okay, I think we all understand what I'm talking about. In other words, Q will be continuous in L2 if and only if the quadratic part of beta converges to 0 as kappa goes to infinity uniformly in Q. Okay, so really these new conserved quantities hold the key to equicontinuity. Now, where does this 4 pi assumption come in that I mentioned earlier? Well, the problem is that it's not beta 2 that is conserved, it's beta that's conserved, right? So my problem is that, okay, so I start with a set that is continuous, which means that beta 2 for the initial data converges to 0. But, and I want to show that beta 2 at later times also converges to 0. So the difficult part is controlling the difference of the rest of the tails of the series, right? That is the hard part, and that is exactly where we need this 4 pi assumption. Okay, now, how do we go from that to global well-posedness? So for that, we use, once again, our favorite conserved quantities, alpha, and the method that is now known as the method of commuting flows. So our conserved quantities alpha admit the following asymptotic expansion, where we see as the coefficients of these negative powers of kappa to be very familiar. They are exactly the previously known polynomial conservation laws. Okay. So looking at this asymptotic expansion, we get inspired to consider h kappa like this. H kappa to be 4 kappa times the real part of alpha. Why? Because this is exactly the Hamiltonian of the NLS, h, plus some lower order terms. Okay. So what do we have? We have this Hamiltonian that as kappa goes to infinity, approaches the Hamiltonian of the NLS. Okay. On top of that, the Hamiltonians h kappa and h define commuting flows. So if I take some initial data and flow it for some time under the H kappa flow, and then for some other time under the DNLS flow, I will get exactly the same thing as if I had done these two different things in the opposite order, right? Moreover, the results that I mentioned earlier, the continuity result and the H's bounds results hold also for the H kappa flow. So I also have this continuity results and the a priori bounds for these. Now it is, for these equations, it is much easier to prove global well-posedness. Actually, we can prove global well-posedness in HS for S greater or equal to 0 for those. And then the hard part, and our hope, is that these flows are actually going to converge to DNLS as kappa goes to infinity, and then use the global well-posedness of those and this convergence to so that DNLS inherits the convergence, the global well-posedness as well. Okay. Okay. So a few words about that. So we look at the flow induced by the difference of the Hamiltonians H and H kappa. And we want to show that this will converge to the identity as kappa goes to infinity. And in fact, we need to prove a result like this. So we want, if I take some initial data Q and I flow it under this difference flow, I want it to converge to the identity in HS, and I want this convergence to happen uniformly in time and uniformly on the set Q, which is going to be a bounded and continuous set. Okay. Okay. So this is what we prove. This is the harder part of the proof, and this is precisely where the S greater or equal to 1/6 assumption that I mentioned earlier was required. And the reason is the following. Okay, so we had DNLS, and now we subtract this H kappa flow from that. DNLS had this cubic nonlinearity, and this will not go away still for the difference flow. So we need to make sense of this cubic nonlinearity. So we need Q to be in L3. And how do we make sure that this happens? It has to be in H1/6. Okay. Okay. So now, how does this allow us to prove global well-posedness for DNLS? It allows us to control differences of solutions. Okay. So if I take two initial data, Q0 and Q0 tilde, and suppose that Q and Q tilde are the corresponding solutions to DNLS, then I can split this difference as follows. So again, the difference of the two solutions to DNLS, I can split it as the difference of solution to DNLS with initial data Q0 minus solution to H kappa with the same initial data, plus the difference of H kappa solutions for two different initial data, plus the difference of solutions to the H kappa and to the DNLS equations, again with the same initial data. Okay. So what do we have? The first one, it is going to converge to 0 because the H kappa flow, the difference flow converges to the identity, right? The second one is going to be very small because the H kappa flow is globally well-posed. Okay, so if my initial data were close enough, this is going to end up close enough. And then the last one is also the same as the first one because I have that the difference flow converges to the identity. Okay, so I can control differences of solutions. So if I start with some initial data, how do I define my solution? If I start with some initial,
Can you go back on?
Yeah.
But okay, above is Q. So you're saying this is capital Q is the yeah, it was the closure under the evolution of this H kappa.
Q is this one.
Yeah,
the capital
big
Q.
Q.
It's any bounded continuous set of initial data.
Right, but this evolution of H kappa preserves that.
It preserves the fact that it will be a continuous. It won't be the same set, but it will be a continuous.
It will continue.
Yes, exactly. So at the end of the day, where we will want to apply this, it will not be the set of initial data. It will be the set of evolutions of this initial data. Right? At the end,
moving.
Yes, and that's exactly why we had to. Everything had to be done, not with just. We didn't prove that the orbit of one initial data is a continuous, but if I take an equicontinuous set, the evolution will be continuous as well. Okay, so now if I start with some initial data Q0, how do I even know that the solution exists to the DNLS? I know. So I take a sequence of initial data, Q and naught, that are very nice, are sparse, and I know that those have solutions. And I want them to converge to Q naught in HS. Then, okay, so for any P positive, the corresponding solutions to DNLS are going to converge in HS because of what we saw earlier, uniformly in T. And that is exactly what we're going, the limit of those Qn at time T is exactly what we're going to define as the solution to DNLS for initial data Q naught at time T. And the two limits that we're going to get if we consider two different sequences of initial data that converge to Q naught is going to be, again, exactly the same. Okay, so we have a limit, it is unique, so this is exactly what we define as our solution. Okay, so the sense in which we say that we have global well-posedness is that the data to solution map extends uniquely from Schwarz space to a jointly continuous map. Okay, so this was a very rough sketch of how we proved global well-posedness under the 4π assumption in H16. Now, as I said, other people did the hard work of removing the 4π assumption. So now I want to focus a little the rest of the minutes that I have to how we can go towards critical well-posedness. Okay. What do we have to change? So we already saw that the H kappa flows are globally well-posed in L2. We don't have any issues with that. What part of our proof do we want to change? Part that we want to change is this, right? The convergence. The convergence of the difference flow to the identity. This is exactly where the 1-6 condition came up. But well, we could have done, but we could have done that at the beginning, right? So what we need here is some additional regularity on Q, so that we can even make sense of the nonlinearity. And where does it come from? That comes from local smoothing. So local smoothing tells us that locally in space, on average in time, we gain some amount of derivatives. For the analysis, have a derivative, okay? And that is a dispersive phenomenon, okay? So we have high frequencies moving faster than low frequencies, which means that if you look at the compact interval in space very fast, the high frequencies are going to leave that set. So we will be left with the low frequencies, which are more regular. A problem here is that we don't have local smoothing. So look at this example. So if I take another soliton solution of this equation, the stationary soliton, so here this doesn't move. So we can already see that this is going to pose a problem to local smoothing, right? Nothing moves. It doesn't move, it oscillates. So if we look at the stationary soliton and we rescale that, we're going to get a family of solutions that have the same L2 norm. I just rescaled it. But my local smoothing norm is unbounded, okay? So we cannot get a local smoothing result. L2 boundedness alone is not enough. So instead, we will prove local smoothing not for L2 bounded sets, but for L2 bounded and equicontinuous sets. We also need this extra ingredient of equicontinuity. In addition, local smoothing for DNLS is not enough, because if I go back to what I want to show, what I want to show here, it does not involve DNLS by itself. It involves the difference flow. So I don't want just local smoothing for DNLS, I want local smoothing for the difference flow as well. But well, here it should be a little bit concerned, because as I said, local smoothing is a dispersive phenomenon but for the difference flow, what I claim is that it converges to the identity. So nothing should be moving, right? So how do I prove local smoothing for that? So what we need to do is discover some residual dispersion at high frequencies for the difference flow. So group our terms in a smart way together, exhibit a lot of cancellation, and that's what is going to give us this local smoothing. Okay, so we get this local smoothing result both for DNLS and for the difference flow. I wrote the results for both of those here. So as we said, very important, we need our set to be not just bounded, but also equicontinuous. Okay. So a little bit about how do we prove local smoothing. Once again, we have to use our new conservation laws, alpha. But instead of the original form that we saw it earlier, we have to use a microscopic version of these conservation laws. Like this, we have one for DNLS and one for the difference flow. And then we multiply by,
So alpha was this Fredholm determinant?
yes,
Okay.
well, it was the logarithm. The determinant.
Okay.
Yes. Okay, so we need to use this microscopic conservation law, but once again, alpha is the key to proving logarithm. Okay. And once we get local smoothing, then we have not the same result as before about the convergence of the difference flow, but a localized version of that, right? So locally, we have convergence into uniformly everything we wanted before. So it allows us to control not differences of solutions, but local differences of solutions locally, right? Okay, but what is going to happen? That will take care of our issues locally. What happens towards infinity in space? For that, we're going to need something more. We need to prove a tightness result. So we prove something like this. If I take some positive time t and a set of initial data that is L2 bounded, equicontinuous, and tight, then if I look at the collection Q star of all the future evolutions of initial data in Q, that is also going to be tight. So this is going to take care of what happens at infinity. Okay, thank you very much.
Thank you. So I will take questions, maybe first from the in-person audience. Is there some questions? Yeah, Michael.
Okay, so can this result be used to prove some kind of can be used? So you need just summarize an equicontinuous L2 set of. Is there some random set which can be? Is there some equicontinuous set where you can put some random measure and then study the corresponding statistical properties of solutions? Like white noise, I don't think so. Right?
Yeah, I don't think white noise, but I don't know, maybe. I mean, that sounds very interesting. For sure, but
because you know that the white noise for a periodic KDV is preserved, right? For
yes.
example. And then that was an interesting result. So for NLS, I think there is something on the line, but I forget a little bit. But for VNLS, I don't know.
Yes, from what I'm not aware of any work in this direction. But it's certainly interesting.
And these Fredholm determinants are the zeros of the Fredholm determinant with respect of k, kappa, of any importance? So there's some kind of eigenvalues?
Yes, they are essentially the reason why this 4 pi was there.
Okay.
Right? Yes. So essentially
So,
what
okay.
they
Well,
yes.
is there a heuristics or some explanation of why 4 pi?
Well,
something?
the algebraic soliton, I guess.
Yeah, okay, but-
Yes. But
I guess there are multi-soliton solutions that can have arbitrary L2 norm, no? Why then?
yes. So okay, maybe I can tell you that essentially what they did. I don't have to do that. Okay, so what Ben, Rowan, and Monica did was essentially finding the zeros and removing them one by one to be able to
Some
remove
Blaschke
the
product or something?
Yeah.
Okay.
Yep.
So you need to estimate how much they grow at infinity. Okay, what is the rate, right?
Yes.
And so the analysis on higher dimensions, like to
Forget about.
Well, I guess in that situation, it's not even. I'm not even sure what it would look like, right? Where does the derivative go?
yeah,
I also don't know which one would be physically relevant. But also, yeah, I should say that all of these integrable equations, a lot of them have higher dimensional analogs. But even for the ones that we're sure that like they're interesting and well studied, it's very hard to study. But yeah, that's being able to say something about completely integrable equations in higher special dimensions is definitely something we're looking into.
Are there any questions from the online audience? Can you hear me? Oh, yeah. Hi, Namir. Are you speaking? You're muted. Okay. Anybody?
Oh, I'm fine.
We cannot hear what you're not saying.
Anybody have a question? Any more questions here? I guess I have a question, but maybe I can ask you later. So let's thank Maria again. And I just want to remind people, so next week the talk will be at the CRM. Our speaker Liz is here, and following the talk in the analysis seminar, so we're at the usual time at 2, and then at 3:30 there's a colloquium also at the CRM. So that was in the announcement. I'll send a reminder. So I hope everybody will come. Okay, thank you. And we're still being recorded because I have to get Chris to this.
Yeah, that, maybe, so I know, it's not much of an idea. Yeah.
Well, I think before he was in but after questions, they usually do like a YH section, that thing, so that's my recollection, is that there's basically nothing before now. Like you said. Yeah, after that, they always prepare something, but I think now before, they used to have like sort of keys and copies. Names.
Up to the level.
Not specifically derivative, it's just MLS.
Yeah, I also have a media to get a lot.
So
Are you walking back right now? Okay.
So we can include some randomness, but also send the genus so that we get some down gap structure that you important questions there is first round to choose